Hey everybody, here we are again, more Geodesy fun. So today we're going to start looking at how to calculate the area of a quadrangle on the ellipsoid, which is a little bit different than on the sphere. But to do that, we first have to consider the length along a meridian of longitude from one parallel to the next. So if we're looking laterally at the equator, here's the equator, and up here is the pole. Need to have more colors to choose from. Here's the pole. And let's consider, since we're looking laterally, the blue silhouette of the ellipsoid is actually a line of longitude, right? Just like if we were looking laterally at a sphere. So consider that we have 2 points on the same longitude, but at different latitudes. And we'll call them points A and B for simplicity. And we talked about before how an important element of the ellipsoid when considering radius, different radii we can consider. One of them is is M, which you write it up here. Remember that M is the normal vector at a point, and the length of M, or the magnitude of M, is the radius of curvature. Radius of curvature at that particular point. And we talked about the uniqueness of that within a quadrant. Curvature. So if I draw those, then remember I have, let's see, A would maybe be, that would be, oh, those lines don't show up very well when I try to make them nice and straight, so that would be the radius of curvature at point A. And then B would be wouldn't quite meet. Remember, they don't meet on the spin axis, do they? So MB. And it would be easy to show, I'm not going to derive it right now, but the change with respect to phi. So here is the phi of B, and here is the phi of A, the geodetic latitude. So the change of G, I should probably tell you what G is. That's what we call the arc length along the meridian. So that distance here, the arc length, is G. So the change in the arc length with respect to the geodetic latitude is equal to our radius of curvature. And if I just rearrange the terms, I get dg equals m d phi, right? So then our goal is to solve for G, the arc length along the meridian. And to do that, we would integrate both sides to get G equals the integral of M with respect to phi. That doesn't look so bad, does it? But let's fill in M. So if I were to expand that by the definition of M, we have G equals the integral of, and since I don't have it memorized, A, or the length of the semi-major axis, times 1 minus the eccentricity, I'm using epsilon, squared, over 1 minus epsilon squared sine squared of phi. And we take all of that, to the 3 halves. And all of that with respect to phi, the geodetic latitude. And in big red letters, I'm going to say yikes. Yikes. That's a big integral. That's a really difficult integral to solve. In fact, I'll clue you in on something here. I dare you to try to solve it because that integral, that is an unsolvable integral. Well, that's never fun. Except in the sense that we don't have to solve it. That's kind of fun. And I'll scoot that up a little more. So how are we going to get that value then of the arc distance? Well, we're going to use an infinite series. So we use an infinite series, and I'm going to explain what that is in just a minute. To solve for G. All right, let me go back to my diagram here, and I'm going to tell you how we're going to do that. Let me erase what I have so far. Erase too much, so that's my equator. Now, solving for G, we're not going to do it directly. What we're going to do is we're going to take, so I'm going to come way out here and do this. So the arc distance from the equator to A along the meridian, and we're gonna calculate that, and then we're gonna subtract the arc distance to B along the meridian from the equator. This we'll call S sub A and S sub B. We've been using S quite a bit for arc length. So S sub A is the arc length along the meridian from the equator up to point A, and similarly for B. So we have S sub A, S sub B, and there's G. So my diagram, because I'm such a great artist, is a little difficult to follow. So I did post on Canvas a neater diagram that you can print out to have for your notes. And I put the formulae we're about to go over on that diagram. So you should print that out and 3-hole punch it and put it in your notebook. Okay, boy, a lot of work to do. And I'll just write up here, we need to solve for S sub A and S sub B. And if we do that, then G equals S sub A minus S sub B. And that's how we're going to use an infinite integral, an infinite series. Now, infinite series, we study that in Math 253, which is not a prerequisite for this course. And So I don't expect you to know what that process is or even what an infinite series is. So I'm going to give you a little synopsis of all of Math 253. Not really, just the parts we need. So, infinite series. Whenever we are faced with a function such as logarithm, natural log, so I'm just going to write down, we can use, we can use an infinite series, I'm just going to say IF, to solve functions that are not, I'm paraphrasing here, not readily solvable by, and in quotes, I'll say traditional means or the math tools we're used to. And in fact, computers, calculators actually only use infinite series to solve things like trig functions and integrals, derivatives. So some of the functions we can solve for using infinite series would be the natural log, any trig function, sine, cosine, tangent, secant, blah, blah, blah. Integrals, etc. Many others, many more. And it's a pretty cool method. Let's see, so in short, very short, in short, an infinite series is an, not n, is the sum of an infinite ordered set of terms. And I'll do of terms. There's no E at the end of terms, but my handwriting is not working well today. So for example, if I were to consider, let's see, the sum of, let's see, n equals 1 to infinity of 1 over 2 to the n. And that would look like 1 over 2 to the 1 plus 1 over 4, which is 2 to the 2, plus 1 over 8, plus 1 over 16. I think I need to turn my tab a little bit. I'm writing kind of wonky. Plus dot, 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 plus 1 over 2 to the n plus dot, 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 on for infinity. And if we could carry out that summation for infinity, we would find that this particular series equals 1. And one thing we'll note is that in this particular circumstance, it's not always the case, but in this case, our terms are getting smaller and smaller, right? Well, sometimes that's not the case. There are series that do not eventually get you to any unique solution. So if the sum of a series has a unique solution let's see, we say that it converges. If not, so cases where it wouldn't is if we add up a series and the interim solutions bounce back and forth between, say +1, -1, or between, 2. We're never going to land on a unique solution, so that would diverge. Another case where it diverges is if we can add forever and ever and ever, ad infinitum, and it just never approaches a single number. If we add more terms, eventually it's going to supersede all of the interim terms, and that's always the case. So that would also diverge. So if not, we say the series diverges. And there are some examples of some very powerful and famous and widely used infinite series. So we have, I'm just going to list them. I'm not going to give them to you, but let's see. We have the geometric series, which does not converge, generally speaking. Let's see. We have a power series, which is actually a super category of series. There's several series that fall in the category of power series, some of which are Taylor series. And we use Taylor series in map projections pretty extensively. We also have a Maclaurin series. That's a pretty powerful one. And we also have a binomial series. And that's the one we're going to use, the binomial series, to solve for that integral. And I'm going to do some more writing here. Let me move it up. So now it's important to note that in practice, we cannot actually add an infinite number of terms. But think about what happens as we add more and more terms to our series. We actually are we're closing in on a solution, right? The more terms we add, the closer we get to an actual solution. So thus, we often add only enough terms to arrive or compute at a solution that is within a desired precision or desired level of precision. Something we have predetermined, right? So if we want, if we are working with meters, for example, and we only require a precision to the nearest millimeter, the third decimal place, then we only need to add enough terms to get there. So where does that leave us? So we will use and how shall I say this? We will use a truncated, so a limited number of terms, a truncated binomial series expansion to solve the integral for S. And S, remember on the diagram, S is really G, but taken starting at the equator and going to the point, right? That's our meridional arc distance. Okay, so let's do that. And I'm just going to throw it at you, throw the series at you, and that's what we're going to use. Think of it like a formula. So we can say S, the meridional arc length that given at some latitude, you know, we're starting at the equator and going to S, which has some latitude, that equals A, which is the A we've been talking about, the length of the semi-major axis, over 1 plus this funny looking n, which is called an eta. And I'm going to define eta in just a second. It's not that complicated, but so A over 1 plus eta times, and here is where our infinite series is, A naught times phi minus A sub 2. And these are different A's. Don't think of these are not A's that represent the length of the semi-major axis of the ellipsoid. These are a completely different animal. It's just A is what's used prevalently in an infinite series for the coefficient of the term. Let's see, so minus A sub 2 times sine of 2 theta, or phi, sorry, I do that a lot, plus A4 times the sine of 4 times phi, minus, I'll skip down here, minus, still in the brackets, A6, A sub 6, you'll see a pattern here probably emerging, times the sine of 6 times phi, plus A8 times the sine of 8 times phi. Probably saw that coming. And it turns out that is how many terms we need to get to whatever desired precision we need. So only 5 terms in our infinite series. So it's not really infinite. We're truncating that series with just 5 terms. So I'll say where eta equals f, which is our flattening, over 2 minus f. And we know what that is. We know what it is because we know how to calculate f. It's just a minus b all over a, right? So that's a knowable number. We have our a and our b, our ellipsoids. We're always working with a knowable ellipsoid, right? Okay, so I think probably the best way to show this is just with an example. I'm going to leave that formula up here. And let's see, if we're given, let's see, how do I want to do this so it makes sense? So, okay. I'm just going to say consider, change colors. Consider a quadrangle on the ellipse. And I'm just going to say it's a quadrangle. It's an easy quadrangle. It's, we're just considering a quadrangle that has meridians as the sides and latitudes as the top and bottom. We're not going for any funky diamond-shaped, rotated region. So just a plain simple quadrangle on the ellipse. And so such that the southeast corner of the quadrangle has coordinates phi equals 42 degrees, 15 minutes, 00 seconds. And lambda equals 121 degrees. Oh, that's north. The phi is north, of course. 52 minutes and 30 seconds west. Let's see if I can just draw this real quick. So we have a quadrangle. We have latitudes for the sides. We have meridional arcs for latitudes for the top and bottom. This would be our phi north, and this would be our phi south, and this would be our lambda east, and our lambda west. We need to know how big this is, right? So let's say we go along 7.5 minutes. So 7.5 minutes, I almost made that a second, of latitude. Or sorry, 7.5 minutes is our delta lambda, our difference in the longitude. And it's ellipsoidally square, if I can say that. I don't even know if that's a term, but we're also going through 7.5 minutes on each of the changes in latitude. So now we can calculate the coordinates of each of the corners, couldn't we? We just add 7.5 minutes to our southeast corner, and our southeast corner has our phi lambda as above. So that's what we're going to do. And we want to calculate this distance here. And we already know how to calculate this distance here, right? We went over that. So if we calculate the meridional lengths, and we already know how to calculate our lengths along a parallel of latitude, we have all of the dimensions of the quadrangle. Next step, move it up. Keep some of that here. And just to keep my terminology consistent, I'm going to say that delta lambda equals delta phi, which equals 0 degrees, 0 minutes, or sorry, not 0 minutes, 7 minutes. 7 minutes and 30 seconds. There we go. I have everything. Okay. And in order to perform any calculation on an ellipsoid, we need to know how the ellipsoid is defined, don't we? So we're going to use the Clark ellipsoid of 1866. Wherein we can look up those parameters anywhere, and what it is, it's A equals, And once again, I don't have it memorized. 6,378,206.4 meters. And B equals 6,356,583.8 meters. And so we have everything we need right there in front of us to solve this problem with that infinite series expansion. So let's do that. First by scooting up there we go. When we plug these values, this A, in and our phi, our parallels of latitude, we find that S of phi south equals 4,679,191.797 meters. And S of the north equals, remember S is the distance from the equator along the meridian up to the specified latitude. So that distance, so 4,693,076.532 meters. And we perform that subtraction. Well, I have the bigger number on the bottom, so we would get a negative. But remember, we're talking about magnitudes. Magnitudes are always positive, so we just give the absolute value. And that's going to be equal to 13,884.735. And that's what G equals. So that's the arc length between our 2 points. And I know what you're wondering. You're saying, hey, that's a really crappy example because I didn't show how I did it. So I did it with a spreadsheet on Excel, and I did post this, this example on Canvas. So you can reproduce this spreadsheet using my numbers in order to get the solutions at the bottom, and then all you have to do is in a knowledgeable way plug in your numbers to get an arc distance, that G. Let me pull up that spreadsheet so you can see what that looks like. There it is. And I think what I need to do is I need to post the formulae, this image of the formula I have in the spreadsheet on Canvas, so you can include it on your spreadsheet. It makes it really nice to just look up here and follow and create your formulae. So up here I have my givens. Let me just there. Up there we have our given values. This is everything we're given. Up here we have our formulae. And so I'm just down here, I just lay out what my given values are and convert them to radians. I compute my flattening. I have my Clark ellipsoid values. I compute my flattening and my 1 over f. And we're not actually going to use 1 over f, but it's just, I always do it. And then I have my south latitude in degrees, decimal degrees, and radians. That's just the same as above. And then I compute my my north latitude of my quadrangle by adding that 7.5 minutes. Remember doing all my math in radians, then converting back to degrees, minutes, seconds, so I can see, you know, does that make sense? And then once I have all of those, I just perform my computation. It's convenient, rather than trying to put everything in one cell, to perform some computations off the side. So eta, which is my f over 2 minus f, I have computed here, and you can see my equation up at the top there. And then I computed my A naught, my A2, my A4. And these are actually the not, let's see, these are A naught times, well, I'm just going to say it's the first term. It's not really my A naught. First term, so one term, and this is my second term, and my third term, and fourth term, and so on. That would be misleading if I just said those are my A values. Because I did include the signs of the phi values, all that in here. Did I or didn't I? You know what? I was right the first time. So let me just Control Z all those. Those are my A values, my coefficient terms. And then, so I've calculated all that from our formulae here. And then in the cell, down at the bottom there, the S of the south latitude, I perform my function on each of my A naught, A2, A4, A6, and then following that formula for S sub phi up here at the top. And that's where I get that. Whoop, come out of there. I do the same thing for my north latitude. I take the difference, and look at that. I get my my arc length between or along that 7.5 minute quadrangle on the ellipsoid. So that's all there is to it. It's really not that complicated. The hardest part is just making sure you get your formula right. So again, I'll say I posted this on Canvas. You really should try to reproduce this, and then reproduce it in a way so all you have to do is plug in your coordinates of your southeast corner, your change in your latitude, your change in your parallel of latitude, which I didn't, or the change in your longitude, the change in your parallel of latitude, which I didn't calculate the parallel of latitude here, the arc distance, because we've done that plenty of times. So that's that. And once we have that, we are ready to calculate the area of our quadrangle on the ellipsoid. And let me shrinkify that. Okay, so for this, let's see. I'm just going to write it down. I'm not going to derive it, but we've gone over why. This is from integral calculus. So we can say that if we have an area, it's a funky A. The change in the area is equal to the change in our meridional arc length, and this will make sense if you think about it, times d phi, which we're just going to call L. Just the length of the, let's see, m d phi I should say is, this is m d phi, the measure d phi. So the length of the arc between two meridian lines along the same parallel. So if I were to draw that out, here's our quadrangle on the ellipse. And we have G over here and G over here, which are going to be equal, right? That's a 6. It's been a long day, right? G over here. So this is L up here, that length. And that happens to be L along the north parallel of latitude, and this is L along the south parallel of latitude. And that makes sense. Look, we're looking at the change in g times the measure between the latitudes, or L. So that's length times width. That's how we calculate the area of a square or a rectangle, right? Same thing, but since we have some other complicators in that we're working on an ellipsoid, it's not going to be quite as convenient as working on a plane, of course. So to get that solution, we need the integral. We need to take the integral of dA and the integral of dg times L for whatever latitude. And that'll give us A equals this, and I'm going to plug in the integral of g, and I'm just going to plug in my, let's see, g from what we said before. I'm going to plug in my values. Might as well do it here, right? I'll plug in my values. So for g, remember from the very first start of this session, we said g is equal to m d phi. And going way back, a couple of lectures ago, we know that the measure along any latitude is m cos phi d lambda times the change in the longitude. Whew. And if I rearrange that and work it out, we actually end up with a double integral. We need to consider the integral from phi 1 to phi 2 times, or double integral times the integral from lambda 1 to lambda 2 times mn. And you can go back and see where I get this. You can derive this actually pretty easily. Cos phi d lambda d phi, because we have a double integral. We need two d's at the end, right? And this is solvable. But we're not going to go through solving it. That would be really rigorous, and that would be torture. And I'm not going to make you do it either. Don't worry about that. You don't have to try, unless you want to figure it out. I fully encourage that. But I'm just going to give it to you. If we were to solve that integral, what we would come up with is A, and this is what you do want to recognize, equals lambda 2 minus lambda 1 times A squared times 1 minus the square. Hey, hi, my dog just got in my face. Over 2. I'm going to make a big multiplication here. That's just a times. I think I'm going to need to scoot this over a bit to fit it all in. So times sine of phi over 1 minus epsilon squared, or eccentricity squared, sine squared phi. And I'll just write up here epsilon equals, that's an ampersand, not an epsilon. I'm just redefining it, is first eccentricity. So sine of phi over 1 minus epsilon squared, sine squared phi, plus 1 over 2 epsilon times the natural log of 1 plus epsilon sine phi Don't worry, it will end eventually. Over 1 minus epsilon phi. 1 minus, or epsilon sine phi. And that is evaluated from our first parallel of latitude to our second parallel of latitude. Whew, that's a lot. But let's try to simplify this a little bit if we can. If we look at the two terms, and this is why I put that big multiplication symbol between. If we look at the first one, what do you recognize here? That is not going to change. We're not evaluating between two lines of longitude there. We have lambda 2 and lambda 1 right in the term. So we call that the left quantity, just to make the calculation coming up easier, because we only have to do it once, right? And this one, we need to evaluate. This is the right quantity. And we evaluate for each parallel of latitude. Over here on the left quantity, we just evaluate it once. See, just for clarification, I'm just going to say this left quantity does not change with the change in phi. That's why we only have to do it once. Then move up. Then A equals the left quantity times the right quantity evaluated at phi 2 minus the right quantity evaluated at phi 1. What could be easier than that, right? Just a number on the left multiplied by the difference in the numbers of the right quantities. All right. Let's see. Good time for another example. So for our example, compute the area on the Clark ellipsoid again. Ellipsoid bounded by phi south, just put an S there, equals 30 degrees, 0 minutes, 00 seconds, north latitude. And the north latitude, as opposed to the latitude on the north, as opposed to the north latitude, is what? Is 30 degrees, 03 minutes, and 00 seconds north. So north latitude, south latitude, and then between lambda on the east equals 75 degrees. West longitude. And lambda on the western side of our quadrangle equals 75 degrees, 02 minutes, 00 seconds west. And when we do that, oh yeah, Clark ellipsoid A equals 6, 3, 7, 8. I should have these memorized, but I don't use Clark for anything, so I don't. 0.4 meters, and B equals 6, 3, 5, 6, 583.8 meters. Okay. So when we go through that calculation that we did up here using that formula for A, here, when we go through that calculation, because we have all these values, right? We have our longitude on the west and east. We have our latitude on the north and south. We have A. Yep, we have everything we need. We have B. So we have A and B, so we know how to calculate our epsilon, our eccentricity, first eccentricity. And so when we do that, and that's a simple plug and chug, we get solution. Left quantity equals 11,753,674. These huge numbers. 805. Big numbers. 805.19 meters. I'll just say for short, that's LQ, left quantity. The right quantity of the north latitude is equal to 1.002646 0839 unitless, and that is RQ. Whoop, that's a phi. Too many symbols that are like, where did that come from? Just get rid of it. I meant to grab my eraser. Okay. So that's our right quantity, RQ, of our north latitude. And then we need our right quantity of our south latitude, which equals 1.0011298. And you get to build a spreadsheet on this and check these numbers. Equals, make sure I got that right since you're going to be using that to check your numbers. 112983049. Yep. And that's the right quantity of phi south. Then the area equals the left quantity times RQ. I did that again, didn't I? I like making phis, I guess. So our right quantity of phi north minus our right quantity of phi south. And when I do that simple math, That's really simple math. I get 17,821,550 square meters squared. So, and that's the solution. I mark it, make it very obvious, and there we go. And I did post an example on Canvas that you can use to try to develop your own spreadsheet. So there is an example. I don't think it's necessarily this exact example. I don't remember what I did. There is an example spreadsheet on Canvas. So when you go through this process, how do you check your answer? Well, this is the exact solution. So I'm going to write that down so we know. This is the exact solution process. But that's a lot of stuff. How do you know if you're right? Well, we also have an approximate method, which is much easier. So you can actually do the approximate method. It's not going to be exactly the same, but it will tell you if you're in the ballpark. So the formula for the approximate method is really complicated. It is A is approximately equal to M times the M, not capital M like the radius of curvature. This is little m for measure. I'll make it more obviously a little m too. Just like we used m lambda for the length along a meridian on the spherical model. So this is the measure along the north latitude plus the measure along the south latitude of our quadrangle over 2, which is just the average of those measures, times g. Well, that's just the average of the north length, the average of the south length, which will give me one number, the average of the two lengths. And I multiply that by the heights, and length times height, that gives me an approximation. So then compare the approximation to the exact, just eyeballing it, no calculations, to the exact method to see if we're in the ballpark. So to speak. So that's how you can check to see if you're even, if you're pretty close, then you probably did it exactly right. So those spreadsheets that I post on Canvas, I do take a lot of time to create those because it can be really daunting for you. I do realize to not have something to compare to. So the plan, like I've said before, is for you to actually mimic those spreadsheets with my numbers, and then once you get that working, plug in your own numbers from homework problems to get the solution to your homework problem. All right. So that is it. So we've gone through the length of the meridional arc length between two latitudes, and discovered that G. So we have a way of doing that, and once we have that, we can calculate the area of a quadrilateral. Anyway, Zoom sessions are happening weekly. Be sure to join if you have questions or concerns or discussion or just want to hear what other people have to say. You most likely will learn a lot from what other people have to say and ask. It's really been a valuable tool to students in the past to keep up and really drive that understanding, that comprehension. So if you can, try to join those weekly Zoom sessions. Also, if that time slot doesn't work for you, reach out and we can set something up for you. I'm really happy to set up individual Zoom sessions when needed. So that's it. Anyway, I hope to hear from you soon, and let me know if you have any questions. Bye-bye.